This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 10 of Week 5, Heat Exchangers, by the LMTD and NTU methods. 2 analysis routes from 1 energy balance, and the whole game is knowing which route a problem hands you. This shows up on virtually every mechanical exam. Start here. Whatever the hot stream loses, the cold stream gains. Heat loss to the room is assumed negligible. Bundle mass flow times specific heat into one term, the heat capacity rate, capital C. Then the balance is just Q equals C hot times the hot temperature drop equals C cold times the cold temperature rise. 1 Q links the 2 streams, and this single equation feeds both methods. Keep one fact in your pocket. The fluid with the smaller capacity rate always sees the larger temperature change. Here is the decision that runs the whole topic. Use LMTD when all 4 terminal temperatures are known. The classic ask is what area is required. Use the NTU or effectiveness method when you know only the inlets, the flow rates, and the exchanger size. The classic ask is what outlet temperatures come out. The tell is in the unknowns. If you'd have to guess an outlet just to start the log term, that's the NTU signal. Choose wrong, and you waste the whole problem. The LMTD method. With every terminal temperature known, the heat duty is U times A times F times the log mean temperature difference. U is the overall coefficient, A its area, F a geometry correction, and delta T LM the true average driving temperature. The correction factor is read from a handbook chart and never exceeds 1. It's exactly 1 for true counterflow and less than 1 for shell and tube or crossflow units. Quietly using 1 where you shouldn't overstates the duty by 10 to 20% and undersizes real hardware. The log mean temperature difference is built from the 2 end differences of the exchanger, delta T1 minus delta T2 over the natural log of their ratio. Which temperatures pair up depends on flow direction. In counterflow, the streams run opposite, so each end pairs an inlet with the far outlet. In parallel flow, both inlets meet at one end. Counterflow holds a more uniform driving temperature along the length, giving a larger log mean and more duty per unit area, which is why most exchangers are built counterflow. Just never let an end difference go to 0 or negative. That means you match the ends up wrong. The effectiveness-NTU method, for when the exits are unknown. First, the most heat the unit could ever move, Q max, equals C min times the inlet to inlet temperature gap, where C min is the smaller of the 2 capacity rates. Effectiveness is the fraction of that ceiling actually reached. NTU is the dimensionless size of the exchanger, UA over C min. And CR is the ratio of the 2 capacity rates. The play, compute NTU and CR, read effectiveness from your geometry, recover the duty as effectiveness times Q max, then back out both outlets from the energy balance. Effectiveness is a known function of NTU and the capacity ratio. For counterflow, there's a closed form, but 2 limiting cases collapse the algebra and appear constantly. When the capacity rates are equal, effectiveness is just NTU over 1 plus NTU. And in a phase change, a condenser or evaporator where one fluid holds constant temperature, so its effective heat capacity goes to infinity and the ratio goes to 0, effectiveness is 1 minus e to the minus NTU for any configuration. That last one is worth memorizing. Otherwise, the handbook prints charts for every layout. On the exam, reading the chart beats evaluating the formula. Variable table. Heat duty Q is the answer. The heat capacity rate, C equals m dot times Cp, and the exchanger size, UA, are given. The correction factor F and effectiveness come off charts. The log mean delta T, NTU, and the capacity ratio you solve for. Almost everything here is dimensionless or in temperature units only, so there's no unit gymnastics if you stay in one system. One discipline though, compute both capacity rates explicitly before labeling C min. A small flow with a high specific heat can outweigh a big flow with a low one. Worked problem. A counterflow exchanger cools hot water with cold water. The hot stream is 2 kilograms per second entering at 80 degrees C. The cold stream is 1 kilogram per second entering at 20. Both are water. The exchanger size UA is 5,000 watts per Kelvin, true counterflow, so F is 1. The exits are unknown, so it's an NTU problem. The plan, capacity rates, then NTU and effectiveness. Then the duty and the two outlet temperatures, and finally a cross-check by the LMTD method. Capacity rates first. Hot is 8360 watts per Kelvin. Cold is 4180. So C min is the cold stream, and the ratio is 1/2. NTU is UA over C min, about 1.2. Feed that into the counterflow relation, and effectiveness is 0.621. The most possible duty is C min times the 60-degree inlet gap, 250 kilowatts, times effectiveness gives the actual duty, about 156 kilowatts. Then the outlets fall out of the energy balance. Cold leaves near 57, hot leaves near 61. Notice the cold stream, the smaller C fluid, climbs 37 degrees, while the hot drops only 19. That's the rule, and a fast gut check. Now that all four temperatures are known, the LMTD method must reproduce the duty. Build the two counterflow end differences, about 23 degrees at one end, 41 at the other. Their log mean is 31 degrees. Multiply by UA, with F equal to 1, and the duty is 156 kilowatts, the same answer. The two methods agree, which means the NTU outlets are self-consistent. That's the whole point. NTU and LMTD are two windows on 1Q equals UA delta T. NTU got the outlets from inlets alone. LMTD re-derived the identical duty as an independent audit. 4 traps. 1. Wrong method for the givens. All 4 temps means LMTD. Only inlets plus UA means NTU. Force the wrong one and you're stuck iterating. 2. Mislabeling C min. Compute both capacity rates, because the smaller mass flow isn't always the smaller capacity rate, and a wrong C min corrupts everything downstream. 3. Wrong end pairing in the log mean. Counterflow and parallel pair the temperatures differently, and mixing them gives an impossible negative driving temperature. 4. Dropping the F factor. It's 1 only for true counterflow, and assuming 1 on a shell and tube unit overstates duty 10 to 20%. Bookmark section 5.5. Both methods live together on pages 299 to 301. The energy balance with capacity rates. The LMTD method and its log mean driving temperature. The effectiveness-NTU groups. And the phase change shortcut. Effectiveness equals 1 minus e to the minus NTU for any condenser or evaporator. Read the handbook charts on exam day rather than grinding the closed forms. Up next in week 5, condensers, cooling towers, and the refrigeration cycle, where the same zero ratio effectiveness shortcut comes right back for the condensing and evaporating sides.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.